Hello students, this video is on epoxides. So we are going to learn about epoxides in this lecture. So this is your syllabus. In module 1 we have to study about epoxides, preparation from alkenes, acid and base catalyzed ring opening reactions in epoxides. So epoxides, these are cyclic ethers with 3-atom ring. So these are cyclic and these are a category of ethers because oxygen is bonded by 2 sp3 hybridized carbon atoms, and this is a 3-membered ring. So there is 1 oxygen atom and 2 carbon atoms. So this is the structure of epoxides, and the carbon atom may be substituted with 2 alkyl groups or even 2 hydrogen atoms. So R1, R2, R3, R4 represents any alkyl or aryl groups. And the compound containing the epoxide functional group can be called as epoxy, epoxide, oxyrade or ethoxylene. So these are different names for this compound. So what is the speciality of epoxides? So epoxides are having a ring structure, and because of this 3-membered cyclic ring, there is a ring strain inside these compounds. So in order to relieve this ring strain, epoxide will undergo reactions with other substances. So the carbon in an epoxide group are very reactive electrophiles, because there is a large part of substantial ring strain, and to relieve this ring strain it is readily subjected to nucleophilic attack from outside. So we can see the structure here. This is the structure of epoxide, and a nucleophile is coming to attack the carbon atom in the ring, and consequently there will be a breakage of the CO bond here, and this ring will be opened and the ring strain will be relieved in this structure. So this is the ring open structure. So this is the 3-membered ring with high energy, that is structure having ring strain. And the second structure, this is a ring which is opened structure, and the energy is released in this structure formation. So here I have shown an energy profile diagram of an epoxide and an ether. Okay, so epoxides are cyclic ethers. So we can see that there is considerable energy difference between these two structures. So because of the ring strain, around 105 kilojoules, there is excess higher energy for the epoxide structure. So when this reactant is subjected to a nucleophilic attack, it will be converted to the product, and the energy state, the relative energy state of the reactant side and the product side can be seen here. So here the ether is converted to an activated state. This is the activation energy, EA. EA represents the activation energy, and this activated state is then converted to the product. And in the second curve, the epoxide, it is converted to an activated state, and then again it is converted to the product. So this epoxide difference between the activation energies of these two is very big. For epoxide, the activation energy is very low. Because of this ring strain, the initial potential energy of the initial ring is very high, and due to this the activation energy is very low here. So it is very easily converted to the product. While the case of ether, there is no ring strain and activation energy is very high here for the transition state structure, and therefore there will be a little bit lag or some extra energy will be needed to overcome this activation energy barrier to convert to the product state. So this is the energy profile diagram comparing an epoxide and an ether reaction. So we will see the synthesis of epoxides. Epoxides can be synthesized by various methods. First is by oxidation of ethylene with oxygen in the presence of a silver catalyst. So this is the structure of ethylene, CH2 double bond CH2. When this ethylene is oxidized in presence of a silver catalyst Ag2O, this oxygen is inserted between the double bond. So the three-membered ring structure is formed. So this is the most important and the simplest epoxide, that is the ethylene oxide, and it is prepared on an industrial scale by the catalytic oxidation of ethylene by air in presence of silver catalyst Ag2O. And ethylene oxide is an important chemical feedstock, and it is used for the manufacture of ethylene glycol, which is used as an antifreeze, liquid coolant and solvent. And this ethylene glycol is in turn used for the production of polyester, polyethylene terephthalate. These are all raw materials used for making plastic bottles and all. So this is a very important reaction. Then second method is by peroxy acid reactions with alkenes. So we can see an alkene. So when this alkene is reacted with a peroxy acid, here I have given the structure of metachloroperbenzoic acid. So this is perbenzoic acid, that is COOH group is there. So the chlorine group is in the meta position. So this is the structure of metachloroperbenzoic acid, and when this alkene trans 2-pentene is treated with the metachloroperbenzoic acid or MCPBA in presence of the solvent CH2Cl2, the extra oxygen atom is substituted, is inserted inside the double bond, and subsequently we get an epoxide here, and we get two epoxide, that is the enantiomer of this structure also. So this is trans 3-ethylene 2-methoxy cyclopropane. So the peculiarity of this compound is that this peroxy carboxylic acids usually have a electropositive oxygen atom, and because of this the reaction is initiated by an electrophilic oxygen atom reacting with the nucleophilic carbon-carbon double bond. Okay, this carbon-carbon double bond is electron rich. So this electrophilic oxygen atom attacks this carbon-carbon double bond. So the mechanism involves a concerted reaction involving a circular transition state, and the result is that the originally electropositive oxygen atom inside the peroxy acid ends up in the epoxide, ends up in the double bond. So oxacyclopropane ring is formed, and the COOH group will become COOH group, that is carboxylic acid group. And in your text there is also a reaction with peracetic acid. So you can write any two reactions. Either you can write this a reaction of an alkene with metachloroperbenzoic acid, or you can write the reaction with peracetic acid. Okay. So there is another alkene. This is a cyclic alkene. Okay, this is a cyclic structure. In this case also we can use a peroxyacetic acid like metachloroperbenzoic acid for the insertion of oxygen atom in the double bond. So this is the structure of the epoxy cyclohexane. This is cyclohexane substituted with an epoxide ring. So this is epoxy cyclohexane. And in this case we can see that an alkene and a peroxy acid is converted to an epoxide and a carboxylic acid group. So this is how this reaction is working. Then suppose if there is two double bonds in this structure, like the structure shown below. If there are two double bonds, so epoxidation works better for electron rich double bonds. That is, the electron rich double bond is attacked by the electropositive oxygen atom inside the peroxy acid. So in this case, due to the presence of two CH3 groups, because of the plus I inductive effect, this double bond will be, the second double bond will be very electron rich. Therefore oxygen insertion will happen in this double bond shown in the red color. Okay, this is the final product. The second, the blue color double bond will remain intact, it will not be affected. Another method is by intramolecular Williamson's ether synthesis through the halohydrants. So in the preparation of ethers we have discussed about Williamson's ether synthesis. So we can recollect this firstly. That is an alcohol, when treated with sodium we get a sodium alkoxide, and this alkoxide ion will again react with an alkyl halide, and we get an ether, and the sodium halide will be eliminated. So similar to this reaction, in the case of epoxides also we can use an intramolecular Williamson's ether synthesis. That is, it is an intramolecular reaction. So we take a cyclic alkene like this, and in presence of chlorine and water we are halogenating the structure. So the OH group and a chlorine group will be substituted in this double bond. So double bond addition reaction occurs. So this is the resulting structure, and this is the second structure. And in the second structure again we are treating with sodium hydroxide, and sodium hydroxide is a base and it will abstract a proton from the OH group. So O minus will be formed. The third structure you can see an O minus. This O minus will attack intramolecularly to the adjacent carbon atom where the chlorine atom is attached. So since chlorine is a very good leaving group, the oxygen atom attack this carbon atom and the chlorine leaves. So a three-membered ring containing oxygen, carbon and carbon. The three-membered ring will be formed. So this is the fourth structure, the resulting structure. So we can see that in this structure there are two rings. One is the cyclopentane ring, and the second is the three-membered epoxide ring. So this is the intramolecular Williamson's ether synthesis via halohydrants. First we make a halohydrin and then we treat with a base. It undergoes an intramolecular attack and forms an epoxide. Then synthesis from halohydrants. When halohydrants are treated with base, an intramolecular cyclization occurs and epoxides are formed. Next method is a very important method, that is Sharpless asymmetric epoxidation reaction. It is a bit complicated, but it's very important synthetic reaction. So here we use a prochiral allylic alcohol. So you can see an allylic alcohol here. So allylic alcohol is prochiral because it can be attacked from two phases, Si phase, that is from the top, and Re phase, that is attack from the bottom phase. So both these attacks will give different enantiomers. That is why this allylic alcohol is called a prochiral allylic alcohol. So from this prochiral allylic alcohol we can prepare 2,3-epoxy alcohol. These two are the structures. 2,3-epoxy alcohols can be prepared. So this is a very highly enantioselective reaction, and we use a catalyst, titanium tetra isopropoxide and diethyl tartrate. So diethyl tartrate can be either dextro or levo, and depending on the choice of the configuration of this diethyl tartrate, we get two different isomers of the 2,3-epoxy alcohol, and we are also using a tertiary butyl alcohol as a solvent. So this is sharpless asymmetric epoxidation reaction. This is also a very important method for the preparation of epoxides. So in your text you can see the properties of epoxides. So we can simply go through that. It's very toxic and flammable gas, and having high boiling point of 287, and it is highly reactive and has a tendency for ring opening. So that is the main thing. Epoxides have a high tendency for ring opening reactions, and the oxygen atom can combine with an active hydrogen atom of compounds like water, alcohol, ammonia, halogen acid, etc. to form a hydroxy group. So a few important reactions are given. In the first reaction, the epoxide combines with H plus in water, and we get an ethylene glycol. The ring is opened. So all these are examples for ring opening reactions. In the second case, a methanol in presence of an acid, we get a 2-methoxyethanol as the product. And if again in another alcohol, ethanol in presence of H plus, we get 2-ethoxyethanol as the product. If you are treating this epoxide with acetic acid, we get 2-glycol monoacetate as the product. Again with ammonia, in the case of ammonia, the ethylene group will be substituted with OH group and an NH2 group. So 2-aminoethanol will be the product. With HBr, this is a halogenic acid. So in case of HBr, OH group and Br group will be additionally added to the CH2 double bond. Then we get a bromoethanol. Then lithium aluminum hydride, this is a reducing agent. It can donate hydride ions to the structure, so the epoxide will be reduced. So hydrogen will be added. So CH3, CH2, OH will be the product. And on heating epoxides, we get ethanol. This is an aldehyde, CH3, CHO. Aldehyde will be formed. Simply on heating ethanol, the product is an ethanaldehyde. Okay, ethanol. And again with the Grignard reagent, CH3MgI, we get an addition product, CH3, CH2, CH2OMgI, which on hydrolysis in presence of an acid gives an alcohol, that is CH3, CH2, CH2OH. So these are the few important reactions given in your textbook. So now we will come to acid and base catalyzed ring opening reactions in epoxide. So ring opening reactions, it can proceed by either SN2 or SN1 mechanism depending on the nature of the epoxide and on the reaction conditions. So first we will look at the acid catalyzed ring opening reaction. So acid catalyzed means this type of ring opening reaction is catalyzed by an acid, that is there is a presence of H plus ions in the medium. Okay, and we say that this is an acidic methanol medium. So we need an acid and we need a methanol, an alcohol. So there is a sulfuric acid and a CH3OH. So acid catalyzed ring opening reactions. When a solvolysis of an epoxide is occurring in an acidic methanol medium, the reaction occurs by mechanism with substantial SN1 character. That is, in this case, the more substituted carbon part is the site of the attack. So this is an asymmetric epoxide. So in one carbon there is two CH3 groups, and the second carbon is two hydrogen atoms. This is an asymmetric epoxide. So the CH3O minus group is the substituent, and this CH3O minus group in the alcohol will come and attack at the more substituted carbon atom, and this oxygen will be converted to the OH group. So this is in the product A, you can see an OCH3 group and an OH group. The ring is not there, so the ring opens. So this is the equation for an acid catalyzed ring opening reaction. An epoxide, when treated with sulfuric acid and an alcohol like methanol, we get the product A. Let us understand the mechanism of this acid catalyzed reaction. In the first step, the oxygen is protonated, creating a good leaving group. So the reaction is catalyzed by an acid. So there is presence of H plus in the medium. This H plus will come and attach to the oxygen atom of the epoxide, because the oxygen is very electron rich, and consequently an OH bond with a partial positive charge on the oxygen will be formed. This is the first step. The oxygen is protonated, creating a good leaving group. In the second step, the carbon oxygen bond begins to break and a positive charge begins to build up on the more substituted carbon atom. So you can see in the third structure, the carbon oxygen atom is partially breaking. Okay, it is beginning to break, and we see that the carbon is acquiring a slight positive charge here. A positive charge built up on the more substituted carbon. And in the third step, the nucleophile attacks the electrophilic carbon before a complete carbocation intermediate has a chance to form. So here the carbon is getting the positive charge, so this is a kind of a secondary carbocation. A carbocation is forming, but before the completion of this carbocation itself, the nucleophile, that is CH3O minus from the CH3OH, will attack the positively charged carbon side through the oxygen. This oxygen is having lone pairs, so this oxygen will come and attach to the this carbon center. So as a result, this CO bond will break completely, and these electrons are shifted to the oxygen atom, and OH group will be free. So the OH is formed here. And again there is a proton attached to the CH3OH. So this proton will be abstracted by another CH3OH molecule, as can be seen in the structure. So the final product is, we get a ring open, a substance where there is an OH group and OCH3 group in the anti positions. Okay, these are in the anti positions. So this is how the product is formed in an acid catalyzed reaction. So the acid is coming and attaching to the oxygen atom first, and this creates a partial breakage of the oxygen carbon bond, and when a positive charge is acquired at this carbon, the nucleophile comes and attack at this carbon position, and the ring completely opens up, and the OH is formed. OH bond is formed here, and the excess proton is subtracted by another molecule in the OCH3 group, and we get the product A. So let us see the carbocation formation here. So the protonated epoxide has several resonance structures. You can see the first resonance structure. In this, the proton from the acid has attached to the oxygen atom, and in the second structure what happens is that the CO bond breaks, and this creates a carbocation here. You can see a carbocation where this is a secondary carbocation where there is a positive charge on the carbon. Okay, and again the next resonance structure is that this OH bond can be shifted here. This OH bond can be shifted here. So this positive charge will go, and the CH2 will acquire a positive charge. Okay, this is the structure. So there are three resonance structures possible. That is why this among these three structures, the structure 2 is a major contributor, because this carbocation is more stable. Okay, so this is a major contributor. It is more highly substituted. Okay, highly substituted carbocation is more stable here. So that is the reason why in the mechanism the coming nucleophile is attacking the carbon having the positive charge, not the other carbon. There are two carbon atoms in epoxide, so the more chances are that since this structure is more stable, this carbocation is more stable, and the nucleophile attacks the carbocation, not the other carbon atom. So let us see a base-catalyzed ring opening reaction. So in the base-catalyzed ring opening reaction, there is no H+. Okay, there is no acid or H+ ions. So this type of epoxide ring opening is entirely catalyzed by a base. And if the epoxide is asymmetric, the structure of the product will vary according to the mechanism which predominates. So in a base catalyzed reaction, we see that there is a presence of NaOH, Na plus and OH minus, and there is presence of methanol. So we say that this is a basic methanol. Okay, basic methanol. So the solvolysis reaction is undergone in a basic methanol medium, and we see the product here is different from an acid catalyzed reaction. Okay, so the molecular formula is same, but the these are isomers are formed. So in the first case, we see that the OH group is in the second carbon and OCH3 group is in the first carbon. But in the case of a base catalyzed reaction, the OH group is on the first carbon and OCH3 group is formed on the second carbon. So when an asymmetric epoxide undergoes a solvolysis in basic methanol, a ring opening occurs by an SN2 mechanism. And in this case, the less substituted carbon atom is the site of the nucleophilic attack. So in a base catalyzed reaction, the less substituted carbon atom here is the second carbon. Okay, these are having two hydrogens only. So this carbon atom, the less substituted carbon atom, is the center of the nucleophilic attack, where OCH3 minus group will come and attack the less substituted carbon atom, and this will lead to the product B. Let us understand the mechanism of a base-catalyzed reaction. So the leaving group here is an alkoxide anion because there is no acid available to protonate the oxygen prior to ring opening. Okay, here there is no protons available to protonate the oxygen atom. Therefore, here the leaving group will be an alkoxide anion from an alcohol itself, and the alkoxide is a poor leaving group. Okay, this is a very poor leaving group, so the ring is likely to be opened without a push from the nucleophile. And we can see the mechanism here. Here a CH3O- group will come and attack the less substituted, that is a less hindered carbon atom at this site, and consequently a ring opening occurs. This electron will be shifted to the oxygen, forming an O-, and the O- will abstract an H+ from another alcohol molecule that we can see here. CH3OH is donating a hydrogen NH+ ion to this O-. Okay, so the OCH3 group forms a bond at the second carbon atom, and an OH, and the O- atom abstract a proton from another alcohol molecule and form the OH bond. So this is a final product where we can see an OCH3 group at the bottom and the OH group at the top. Okay, so here the nucleophile itself is potent, that it is a deprotonated negatively charged methoxide ion. So this is a nucleophile. Nucleophile is deprotonated. We are using a base here. Okay, so base NaOH will be having OH- ions, and this OH- ion will abstract the proton from the CH3OH. So here the nucleophile, attacking nucleophile is CH3O-. This itself is a negatively charged methoxide ion, but remember it is a very poor leaving group. Okay, and this nucleophile is attacking the less hindered carbon atom, and the ring opening occurs. So when a nucleophilic substitution reaction involves a poor leaving group and a powerful nucleophile, it is very likely to proceed by an SN2 mechanism. So that is why, because this nucleophile is actually a powerful attacking agent, but at the same time it is a poor leaving group. That is why this mechanism is proceeding by an SN2 mechanism. This reaction is proceeding by an SN2 mechanism. Okay, in the case of symmetric epoxides, what will happen? You can see a cyclic epoxide here. If the base catalysis is occurring in a symmetric epoxide, so the reaction of hydroxide with an asymmetric epoxide generates anti-diols. Okay, that is the attack is from the back side of the ring. At the top of the ring, the oxygen is hindering the approach of the attacking agent. So the attack will always occur from the back side of the ring, and the OH bond will be formed at the bottom of the ring's plane. You can see this bond here, dash wedge bond here, and the opened ring will have the O-, and a proton will be abstracted from water and forms an OH here. So we see that when this ring opens, an anti-diol is formed. Okay, one OH group is at the bottom of the ring, and one OH group, the second OH group, is at the top of the ring. So this is an anti conformations. Two OH groups are in anti conformation. Suppose if in the place of OH group we have a CH3O-. Okay, CH3O- is a attacking nucleophile. What happens here? Here the first substituent will be an OH and the second will be OCH3 group. Okay, that's the difference. Now let us see this first equation. How can you bring this following chemical transformation? You can see a cyclic alkene, a cyclopentene. We have to convert it to a diol, that is anti-diols. So in the first step, we try to insert an oxygen atom in the double bond. We can use any peroxy acids like peroxyacetic acid or metachloroperbenzoic acid. So using this peroxy acids, we can insert an oxygen atom in the double bond. Okay, and in the next step, we try this acid hydrolysis. So when acid hydrolysis occurs, another OH group will be substituted at the OH will come and attack from the back side of the ring, and consequently the epoxides O group will convert to an OH group at the bottom of the ring plane, and the externally attacking OH group will come and attach from the bottom of the ring plane. So this is the one is at the top of the ring plane and another OH group is at the bottom of the ring plane. So this is the anti-diols. Okay, anti-diols. Then epoxide can be opened up by alcohols with acid catalysis to generate alkoxy alcohol with anti-stereochemistry. So this is the mechanism. Here again, if you are using an alcohol here, ROH, we get an OR group substituted in place of this OH group. Okay, so here also the OH group will be at the bottom of the ring plane, and OR group will be at the OH group will be at the top of the ring plane, and OR group will be at the bottom of the rings plane. So the main point is that the attack takes place preferentially from the back side, like in an SN2 reaction, because the carbon-oxygen bond is still to some degree in that place, and the oxygen blocks the attack from the front side. Okay, you take the structure, and in this case the oxygen is at the front side and it will block the attack of the nucleophile from this side. So as a result, the nucleophile always prefer attack from the back side of the ring. And in an acid catalyzed process, the nucleophile attacks the more substituted carbon because it is this carbon that holds a great degree of positive charge. Acid catalyzed reaction nucleophilic attack occurs at the more substituted carbon atom, whereas in the base catalyzed reaction it occurs from the less hindered carbon atom. So these two are good examples for regioselective reactions. Okay, regioselective means there is a preference for the region of the attack. These are asymmetric epoxides, and if you are using an acid catalyzed mechanism, the region of attack is at the more substituted carbon, and if you are using a base catalyzed way of mechanism, the region of attack of CH3O minus is at the less hindered carbon atom. So these are good examples for regioselective reactions. So in regioselective reactions, two different constitutional isomers, these are constitutional isomers, okay, two different constitutional isomers will be formed, but one will be formed predominantly. Okay, both will be formed to some extent, but in the case of an acid opened reaction, product A will be formed predominantly. In the case of a base catalyzed ring opening reaction, product B will be formed predominantly. So these type of reactions are called regioselective reactions. Here let us see the reaction of an epoxide with a hydrohalic acid, that is HBr. We are taking the example of HBr here. So the epoxide react with the HBr to produce a halohydride. Okay, we have seen that earlier, how we can create a halohydride. Okay, and how this mechanism is proceeding. First, the H plus will protonate the oxygen atom, and the second structure, you can see here, the second structure will be formed. Oxygen will be having a positive charge. Again, in the next step, the Br minus will attack from the back side of the ring. So this will give anti-conformations. OH will be at the top of the ring plane, Br will be at the bottom of the ring plane. And this structure, again, if another molecule of HBr is reacting, okay, second molecule of HBr from the medium itself, if it is coming, this OH group will leave, okay, and this Br will attack. So the Br will attack from the back side here, the first carbon, okay, the carbon where OH group is substituted. Br will attack from the back side and the OH group will leave. So we can see the product here. Here both the bromine are on the same side, isn't it? So these are actually cis dibromocyclopentane. Okay. So in this type of reactions, the cis product will be the major product, and some amount of trans isomer will also be formed, but this is cis product will be the major product. So with hydrohalic acids, we can create this type of products where this two halogens are substituted here. So there is no oxygen atom here. The epoxide oxygen atom is converted to OH. Again, the second molecule of HBr comes and attack, and this OH group is leaving. And again, a second Br will come and attach here. So this two Br is from the same side of the ring plane. So these are cis product. Now let us compare the acid catalyzed and base catalyzed reaction. So we have a unsymmetrical epoxide here. In the case of an acid catalyzed mechanism, we get a product 2-ethoxy 2-methyl propan 1-ol. This is the acid catalyzed product. That is, the OCH2CH3 bond will come and attack at the more substituted carbon atom, because this carbon, when acquiring the positive charge, is beginning to form the carbocation, it will be the more stable structure. Okay, this is a secondary carbocation. Therefore, the product is, and the acid catalyzed product is the first one. And in the case of base catalyzed reaction, here when we use a base, what happens is that the CH3CH2O minus will be formed, as the H plus is abstracted by the base. Okay, and this alkoxide anion prefers a less hindered carbon atom, and subsequently the second product is formed in a base catalyzed reaction. So the ring opens to this side, and the OH will be formed in the more substituted carbon atom. The OH group bond will be attached to the carbon with more substituted carbon atom, and the OCH3 group attacks the less hindered carbon atom, that is the CH2 carbon. So the product is 1-ethoxy 2-methyl propan 2-ol. So under basic conditions, the alkoxide simply attack the least sterically hindered epoxide carbon in an SN2 displacement. Okay, and while under acidic conditions, alcohol seems to attack the more hindered carbon atom, but it is a bit more complicated. That is, the acid H plus first come and protonate the OH, protonate the oxygen atom, and the ring opening reaction will take place accordingly. So these are the difference between acid catalyzed and base catalyzed ring opening reactions in epoxide. Thank you.